All right, so today we're going to talk about the derivative of inverse functions. So when will you use this? You'll use this whenever you want to take derivatives, for example, of the arcsine. The moment we don't know what it is, say the arc cosine. And arc tangent. We'll fill the rest out in a minute, but that's kind of the idea why we're gonna need this. So let's talk about how could we even go about doing such thing. And let's remember what an inverse function, how do we characterize inverse functions. And what we need is that f of f inverse of x will be equal to x for all x in the domain of the inverse function in this case. So for example, when you're taking f inverse to be an arc sine or arc cosine, remember you know that those functions can only be evaluated between -1 and 1. So that equation will be satisfied just on that interval. So, and the arctangent, of course, that one is for -infinity to infinity, so that one there's no problem. But if you go ahead and take the derivative here by using your chain rule, so you take the derivative on both sides, you get the derivative of this one, which is 1. And how do we compute this derivative? Well, by chain rule, we take f prime evaluated at f inverse of x times the derivative of the inside, which is the derivative that we would like to compute, the derivative of the inverse function. So by dividing by this function on both sides, we get that the derivative of the inverse function is going to be 1 over the derivative evaluated at f inverse of x. So if you notice, it's kind of interesting, or quite interesting, that to compute the derivative of the inverse function, you only need to know how to take the derivative of the function itself. So for these functions here, for the arcsine, all you need to know is how to take the derivative of the sine. We know how to do that. And for the arc cosine, we just need to know how to take the derivative of the cosine, and so forth and so on. So that's what this formula will be useful for. So let me record this formula here, and then we're going to go ahead and compute the derivative of the arcsine to get started. So I'm going to record this formula, which is going to be important to us right here. We're going to be referring to it. All right, so let me erase this now that we have it, and we'll compute these derivatives in a minute. All right, so let's go ahead and compute the derivative of the arcsine. So what do we need? Let's write down our functions. So we're going to pick f of x to be the sine, so that the inverse function will be the arcsine. And so now, notice right here, we need the derivative of f, so we compute that, and we get that the derivative is going to be the cosine. So by using this formula, the derivative of the inverse is going to be 1 over the cosine, which is f prime, evaluated at f inverse, arc sine. So now we have to figure out how we write this expression in terms of an algebraic form. So let's go ahead and look at that. So let theta be the arcsine of x. Then what we have is that sine of theta equals x, but what I'm looking for here is just cosine of theta. You see, I wrote theta to be the arcsine, so I need to find an expression for the cosine of theta. So what you need to do is use your Pythagorean identities. Like so, you plug in 1 and subtract cosine square on both sides, and you get that subtract sine square on both sides. You get that cosine square is 1 minus sine squared, but that is x, so it's going to be 1 minus x squared. So we're almost there because I just need to find a cosine. Now remember, when you have this expression, you get cosine is going to be plus minus the square root 1 minus x squared. And now we have to decide what is our sine going to be. And well, if you recall, I'm going to draw it here a little bit small. But if you have your unit circle, almost not quite circle, but let's say it is a circle right now. Remember that you are defining theta to be the arcsine of x. So that angle theta is going to be located between negative pi over 2 and pi over 2. That's going to be the domain that we're restricting the sine so that it becomes a one-to-one function just on that restricted domain, and so that it has an inverse. But if you notice what is going to be the sine of the cosine on that region, well, you are right here. The cosine is the x-coordinate, and as such is going to be positive. So this one is not going to be plus minus, it's just going to be positive. So let me go ahead and write then our result. I'm going to write it over there. And we have that the derivative of the arcsine is 1 over the cosine of theta being the positive square root of 1 minus x squared. So like that, we get 1 over the square root of 1 minus x squared. Looks a lot nicer than all this mess. And this is really what you will have to remember. This is just a way to, I'm just explaining to you how we obtain these formulas. So let me go ahead and fill in the ones that we will need. And this one's going to be 1 over 1 plus x squared. We also need the derivative of the arcsecant, which is going to be 1 over the absolute value of x, and then times the square root of x squared minus 1. Our cosecant would be the negative of this, and our cotangent would be the negative of the arctangent. Kind of don't have room to write them. Let's use this instead, and the other ones you can just look in your book. Alright, so let me go ahead and compute some problems using these formulas right here. And I'm going to do a few examples. I'm going to restrict myself to that board, and that will probably be good for this topic. So let's go ahead and an example where we just have to take the derivative for example, an arcsine of x squared. Let's just do something simple to start. Alright, so from our formula there, notice that we don't have just x, we have x squared. So we have to do a chain rule. So what we're going to do is we're going to write the derivative of f as 1 over the square root of, and instead of x, I'm going to be plugging x squared. So it's going to be x squared squared. Now remember that I'm not plugging x, so I have to pay times the derivative of the inside, which in this case is a 2x. That's the derivative. So when I reorganize it, I just get 2x over the square root of 1 minus x to the 4th. So that right there gives us our derivative. Pretty straightforward. Let's do another one. And I'm just going to give you the functions now. We're just going to compute the derivatives. So for example, we could do a something like this, where you would need to do a product rule before and then use your rule. So in these types of problems, you'll have to use different rules of differentiation, and then you're going to implement these ones at some point. So you do not stop doing your other rules of differentiation just because you're using these ones right here. So here I have a product, so my derivative will have to involve a product rule. So derivative of the first is 1 times the second, and then plus we have the derivative of copy the first times the derivative of the second. Derivative of the second is right here, derivative of the arctangent, so 1 plus x squared. So this one, there's not much simplification we can do. You just arctangent plus x over 1 plus x squared. So those would be 2 easy examples to start. Let's go ahead and compute some more. All right, let's do another one. Let's go ahead and look at the derivative of the function f, where f is going to be given by e to the, say, arc cosine. So we're doing a chain rule, and that chain rule will then involve this formula right here. So our derivative. What is the derivative of e to the x? Is e to the x again. So we copy e to the arc cosine. But I have to pay with the derivative of the exponent. Remember, the derivative of e to the power of u is going to be e to the u times u prime. So derivative of the exponent. So here, derivative of the arc cosine is going to give me a negative 1 over square root of 1 minus x squared. So that would be your derivative. All right, so lastly, we're going to do an example where we use the derivative to compute the equation of the tangent line. So find the equation of the line tangent to the graph of let's grab one of this arc sine at the point, let's pick a point, for example, square root of 2 over 2 comma pi over 4. All right, something like that. All right, so we compute our derivative. The only added difficulty would be that we'll have to do the equation of the line. So first thing is that the slope of the tangent line is going to be the derivative of the arc sine evaluated, I should have written it here, evaluated at square root of 2 over 2. All right, so we compute our derivative, which is going to be 1 over the square root of 1 minus x squared, which is going to be square root of 2 over 2. That is the derivative of the arc sine evaluated at square root of 2 over 2, which in this case is going to be, this becomes, when you square it, becomes a 1/2, because this is the rationalization of square root of 1 over square root of 2. So this becomes 1 over square root of 1 minus 1/2. Now 1 minus 1/2 is going to be 1/2. Square root of that is 1 over square root of 2. The reciprocal of that, square root of 2. So it looks, the slope is quite nice. And all we have to do is write the equation of the line. For that, we use the point slope formula. So we have a slope, we have a point. So y minus pi over 4 is going to be equal to square root of 2 times x minus square root of 2 over 2. And that gives us right there. Then we simplify and gives us the equation of the tangent line.